Hi everyone, welcome to our second video in our series on graph theory. This video will focus on the topic of Euler circuits. So previously we looked at the following graphs and thought about which ones we could trace the entire figure exactly once without lifting our pencil from the graph and start and end at the same point. We saw in particular that for graphs 4 and 5, this was possible, but in other graphs like 1 and 3, this was not. And in this video, we're going to see why, what makes graphs 4 and 5 different than graphs 1 and 3. Now, we also introduced what was called the parking control officer problem. Recall that the officer's job was to check parking meters, and our goal was to find the most efficient route for the parking control officer to walk as he or she checked the parking meters. And to answer this question, we turned our street network into a graph and looked for something called an Euler circuit. So an Euler circuit is a circuit that covers each edge of a graph once, but not more than once. A circuit, recall, means that we must start and stop at the same vertex, because in the case of our parking control officer, he or she needs to return back to their car, right? So we're looking for a path that starts and stops at the same vertex and covers each edge of our graph exactly once. And in this case, here was an example of an answer that we found. Okay, so just to review, what's the difference between a circuit and an Euler circuit? Well, both start and end at the same vertex. Circuits, however, may retrace edges or not use all of the edges. For example, in this graph, we see we start at this vertex, we move to the middle, down, back to the left and up, and then we're going to trace this first edge again in step 5, down, to the right, up, back to the middle, and then we're going to go one more time to get back to the vertex that we started with. So in this particular circuit, we've started and stopped at this vertex here. We've covered this edge of our graph 3 times. So it is a circuit, but not an Euler circuit, because an Euler circuit, we want to travel each edge once and make sure that we cover all of the edges. So here's that example of that Euler circuit on the same graph. We go all the way across, down, back to the middle, around that center loop, back to the left and up. So both of these examples were circuits. They both started and stopped at the same vertex, but only the second one was an Euler circuit because it covered each edge of the graph exactly once. Now let's go a little bit of history. How did Euler circuits get their name? Well, they got their name from a very famous mathematician, Leonhard Euler, and among other discoveries, he was credited with inventing the idea of a graph, as well as the concepts of valence and connectedness that we'll discuss temporarily. The whole field of graph theory came from the following problem, called the Konigsberg bridge problem. And so what happened was, in the town of Konigsberg, the people like to go for a walk. And on Sundays in particular, they like to walk along the town. And here you see there's some rivers that cut through the town, and these green pieces here represent bridges from one land mass to the next. And so the ruler of Konigsberg went to Euler with the following problem. He wanted to know, is it possible for the people of Konigsberg to take a walk through town and cover every bridge exactly once? Now, Euler didn't think this was a very interesting problem at first. He thought that he actually had much more interesting things to be working on, but he was slightly intrigued because he realized there was no mathematics currently in existence that he could use to solve this problem. So he thought he would take a stab at it. And what he decided to do was to replace each land mass with a vertex and to replace each bridge with an edge. So here are our land masses labeled A, B, C, and D. And we're going to let those represent the vertices of our graph. And then we're going to replace each bridge with an edge. So notice there is one bridge connecting the land masses A, B, and C to land mass D. while there are 2 bridges connecting A with B and 2 bridges connecting A with C. And so the question in graph theory terms is, can this graph be traversed without lifting the pencil from the paper and without retracing edges? So you can take a minute and play with this graph, but Euler found that the answer is no. It was not possible. And in taking this approach to the question, this was actually the beginning of graph theory. It was revolutionary at the time to recognize that the size of the land masses and the lengths of the bridges didn't matter. The only thing that mattered was that basic structure. And that was the beginning of what we now call graph theory. So that's your history lesson for today. Back to the math. So when we get around to finding Euler circuits, there are 2 big questions we want to answer. Number 1, is there a way to tell if a graph has an Euler circuit? And number 2, is there a method for finding an Euler circuit when one exists and for finding it quickly? So to answer this question, we need 2 new vocabulary words. So our first, the degree or the valence of a vertex in a graph is the number of edges meeting at that vertex. For example, in this graph, if you look at vertex B, because there are 2 edges coming into that vertex, we would say that B has a valence of 2. Vertex C, on the other hand, because there are no edges coming in there, the valence of vertex C is 0. And then for A and D, there are 3 edges coming in to each one of those vertices, so each of those vertices has a valence of 3. Now, a graph is said to be connected if for every pair of vertices, there's at least one path connecting the 2 vertices. So the graph that we see below is not connected since there's no edge connected to vertex C. Now, if we go back to our example graphs that we've been playing with in the past, there's a vertex highlighted in the lower left corner of vertex 1. What is the valence of that vertex? How many edges are coming into that vertex? Well, it has a valence of 3. As a matter of fact, every vertex in graph 1 has a valence of 3. Let's move on to graph 4. That vertex has a valence of 2. The vertex up top has a valence of 4. The one to the right, a valence of 2. And the one at the bottom, a valence of 4. Now you may remember there was a big difference between graph 1 and graph 4 when it came to finding an Euler circuit. We noticed that one was easy to find for graph 4, but that one did not exist in graph 1. Well, what do you notice about the differences in the valences of these vertices? In graph 4, note that the valences are all even, and in graph 1, they are odd. It turns out that that is the key to whether or not a graph has an Euler circuit. Let's go back to our 2 big questions. So, is there a way to tell if a graph has an Euler circuit? The answer is yes. An Euler circuit exists if and only if the following statements are true. Number 1, the graph is connected. And number 2, the valence of each vertex is even. So, a graph will only have an Euler circuit if it is connected and if the valence of each vertex is even. Our second question, is there a method for finding an Euler circuit when one exists and finding it quickly? Well, the first thing to do is to make sure one exists, right? To check our 2 criteria. Is our graph connected? And is the valence of each vertex even? If the answer is yes, then really the best way to move forward is trial and error. Keep trying to create different paths to find one that starts and ends at the same point and does not retrace steps. Here's another example. Does this graph have an Euler circuit? Well, let's check our 2 criteria. Does it have even valence? So we would look at each vertex. This one has a valence of 2. This one, a valence of 4. 2, 4, 2, 2, 4, 2, 4, 2. All of the valences are even. And second question, is the graph connected? Yes. So Since the answer to both questions was yes, we know that an Euler circuit exists. Now, to find one, we pick a point to start if none has been given. We number the edges in order of travel, showing the direction with an arrow. We want to make sure we cover every edge only once and that we end at the same vertex where we started. So here's our graph. Where should we start? It doesn't really matter. We're going to start at this vertex that we see here. And let's travel, for example, up. And then we can maybe go around this upper triangle. Now we've got to make sure we cover the square on the left. Move all the way across. Up around the square on the right. Finish off with that bottom triangle, being sure that we end where we started. So here is an answer, and here it is written with our edges being numbered, which is a nice practice to do. So notice that we started and stopped at the same vertex, and we covered every edge of our graph exactly once. So we have found an answer, an Euler circuit for this graph. There are many others as well. Here's another example for you to try. If you want a way to get started, there's one possibility. You may want to pause the video and play with this graph. See if you can find an Euler circuit. And here's an answer. There we go. Here's another example for you to try on your own if you like. You can start by checking the valence of every single vertex. They are all even, and this graph is connected. So this graph is guaranteed to have an Euler circuit. See if you can find it. I'm going to move on to another example. Let's consider the following floor plan. The open spaces represent a door that one can pass through. We're going to let the rooms be the vertices, and the connection from room to room be the edges. Let's find a graph, and then an Euler circuit for this graph, letting O represent the outside. All right, I'm going to move my graph over to have some room to work. So our rooms are going to be our vertices. And now let's see. The edges are going to represent doors. So room A has a door connecting to rooms B, C, D, and the outside. So we need one edge connecting A to B, C, D, and the outside. Now B also has a door connecting to room E. C has a door connecting to the outside and two doors connecting to room E. So we need two edges connecting vertex C to vertex D. Finally, we need one edge representing the door from D to E. So what do you think? Can you start at the outside and find an Euler circuit for this graph? Feel free to pause the video and practice before I reveal an answer. So here is one possible Euler circuit. Starting at the outside, we can move to room A, then B, E, D, back to A, C, D, C, back to the outside. So here's one possible Euler circuit for this graph. All right, now how would we prove Euler's theorem? So Euler says that if a graph has an Euler circuit, it must have only even valent vertices, and it must be connected. So this can be proved by pairing up edges at each vertex. For example, if we look at vertex B, we can pair up edges 2 and 3 and edges 9 and 10. So the idea behind why we needed an even valence is that we've got to be able to come into a vertex and go out. Every time we come in, we've got to be able to go back out. So that's the key to the even valent idea. Now, what are some practical applications to Euler circuits? We talked about checking parking meters, also collecting garbage, salting icy roads, inspecting railroad tracks, delivering mail. What are some other ideas you have where you would need to walk along every single road or every single sidewalk? Now, there may be special requirements that need to be addressed. For example, traffic directions, the number of streets or lanes, which would represent divided routes, parking time restrictions. And so there are theory modifications that can be used to address these special requirements. For example, a digraph or a directed graph is used for one-way streets. So arrows show restriction and traversal possibilities, and territories may need to be divided into multiple routes. So here's an example of a route that a salt spreader might need to take, and the graph that you see representing this particular street network taking into account the one-way streets. So examples of digraphs: one-way streets, maybe the steps of a process that must occur sequentially, L trains in the loop that have to go in a specific direction, these types of things. All right, so this wraps up our discussion on Euler circuits, where we travel along every edge exactly once. Up next, we're going to look at graphs where we want to hit every vertex exactly once. Those are called Hamiltonian circuits, and we'll talk about those in the next video. Thanks, guys. Bye.